All right, greetings everyone. So today is the lecture number 5, and today we continue discussing the elements of quantum mechanics, basically the essentials that we will need to go to quantum computing. So yeah, let's start with brief review what we have done last time. Let me see. So we finalized with the linear algebra and then started discussing these basics of quantum mechanics. And we say that we're gonna um, discuss quantum mechanics in form of several postulates. And the first postulate was that quantum state uh, of a quantum system is represented by a vector in a complex Hilbert space, and that in this space the superposition principle holds. That means basically that we can represent a state of any quantum system like this psi as a superposition of several basis states. So this psi vector, this quantum state, is basically it corresponds to some general state of a quantum system. If we're talking about electron, then this state is a superposition of like electrons that propagate to all possible directions. If this is a state of an atom, then this state consists of all possible uh, steady states or energy states in this atom. And if this is a psi of a quantum computer, then this is basically this state includes all possible quantum states of a quantum computer, etc. Right. So then the second postulate, also known as Born's rule, it basically says that these coefficients, these trajectory coefficients of the quantum state psi on a basis states basis vectors in this space, they correspond to the probability amplitudes. These probability amplitudes are complex, and if I want to get the real probability of finding a state in a particular quantum state, then I have to take the modulus square of this complex coefficient. This is what we call Born's rule. And of course, the sum of all these coefficients over all possible states is equal to 1. And I mean, this is because each term here is particular probability, and the sum of all probabilities, of course, gives you 1. So the next postulate says that uh, in order to describe a system, a quantum system, we substitute the classical quantities like coordinates, momentum, energy, etc., by their operators, Hermitian operators in the Hilbert space. So basically, we represent the radius vector by radius vector operator, momentum by its momentum, energy by the operator of energy, which is Hamiltonian of a system. And we will see that actually this Hamiltonian is like very important uh, very important operator, because it allows it gives you a recipe how to describe any quantum system consisting of any number of particles, states, etc. And um, yeah, and the possible results of measurements, like for example, I measure a coordinate or measure energy. So these results of measurement, they are eigenvalues of corresponding Hermitian operator. Like if I measure energy, then what I can get in result in experiment, it will be the eigen value of Hamiltonian. If I measure the momentum, I will get the eigenvalue of the operator of momentum, etc. And and then we said that uh, a system can be represented in different representations. So basically, uh, these Hermitian operators, they not only have real valued eigenvalues, but also the eigenstates of these Hermitian operators uh, provide you a basis. And considering different bases that belongs to different operator, you can represent the same system using different representations. For example, uh, for example, if you consider like a two-level system, it is naturally to represent the system in a energy representation, because in energy representation, the Hamiltonian of this system will be just a matrix 2 by 2 with energies of each single state at the diagonal elements, and off diagonal elements will be 0. Of course, I can describe the same system in the coordinate representation, and then it will be something more complicated. And as an example, we discuss this system, like general system um, in a coordinate representation, and we derive this operator for coordinate, which is simply the product by the coordinate itself. And this is the general rule. If I am if I consider my system in a coordinate representation, then my coordinate operator is just the quantity itself. For example, in this coordinate representation, the operator of a coordinate is just a coordinate. In momentum representation, my operator would be just multiplying by momentum itself, etc. But in this coordinate representation, the operator of a coordinate is coordinate itself, and momentum, the operator of momentum, we derived it in this way. So it is minus I h bar nabla, and nabla is the vectoral operator, basically the sum over the partial derivatives. And yeah, and we stopped at this point. We discussed the Hamiltonian of any system in a coordinate representation. And we say that this Hamiltonian consists of two parts, basically, the operator of kinetic energy and operator of potential energy. So this is like very similar to what we do in classical physics when we uh, describe the total energy of a system as a sum of two, the kinetic energy plus a potential energy. But in this case, this Hamiltonian is kind of yeah, it's a operator of energy of our system. All right, and today we continue this discussion. And so what it was the postulate number 3. So now let's continue with postulate number 4. But before that, let's consider actually a problem, a small problem, just to give you an idea how this works. So let's consider a problem. What are the possible measurement results of a particle with spin 1/2 along x direction? What is the possible measurement results of a particle with spin 1/2. I'm gonna tell you what does it mean. Along x direction. Along x direction. So this is the problem. So so you of course know that there is a quantity is called spin, and for example, if I have a particle like electron or neutron, proton, these small particles, they can be um, considered as a spinning top with like with of course a rotation direction. For example, if this particle rotates, so if it rotates counterclockwise in this direction, right? So I use right hand rule. So if my fingers surround this red arrow counterclockwise, then my thumb points up. So yeah, so this is the right direction. And if it rotates in the opposite direction, I can, I mean, it is equivalent to this spin pointing down. Yeah, and this is true for particles like electron, neutron, proton, etc. And yeah, and this is particle with spin 1/2. Spin 1/2. So yes, so let's consider an electron, for example, in some sort of magnetic trap, and I measure the the spin state of this electron. So this red arrow can point along different directions. So like in this case, it is, for example, z direction. So my electron polarized either upward or downward along z direction, but of course, and I can put my detector along z direction and measure this state along z direction. But of course, I can put this detector along x direction and y direction and measure the state of this spin in the orthogonal direction to the z-axis. And this measurement mathematically is represented by the operator Sx, and it is equal to h bar over 2 sigma x. And sigma x, we already know, this is the Pauli matrix X. So it's equal to H over 2, and poly matrix X is 0, 1, 1, 0. Right? And in order to answer this question, what is the possible measurement results of a particle with spin 1/2 along x direction? That simply, in mathematically, it means that we need to find the eigenvalues of this operator Sx. So in order to find the eigenvalues, what I do, I need to write the determinant of this matrix h bar over 2, 0, 1, 1, 0, and subtract the the matrix alpha 0, 0, 0 alpha. Right. So in result, I'll get another, I mean, a new matrix. Determinant here it will be minus alpha. Here h bar over 2, and then h bar over 2 here, and minus alpha here. And then I have to make it equal to 0, right? So in order to find this lambda, which is the eigenstates of this matrix, I have to find this determinant and make it equal to 0. So what I get, minus lambda minus lambda gives me lambda squared, minus h bar squared over 4 equal to 0. So from here I conclude that my lambda 1, 2 is equal to plus minus h bar over 2. So this is basically the answer. My eigenvalues of this spin operator Sx simply equals to plus minus h bar over 2. It means that in the measurement of spin along in measurement of spin along x-axis, I will get either the result will be plus or minus h bar over 2. And of course, nothing exceptional about axis x, right? I could consider axis y or axis z, and for a system with which is not polarized, I would get the same result for axis y. The result will be also plus minus h bar over 2, and for the z as well, plus minus h bar over 2.
Professor?
Yes?
Question. Yes, okay. So for the z and y, are we gonna say using the same matrix?
No, yeah, it will be for the
A different one. Yes. Okay.
Yeah.
Okay. Okay. I will verify that later.
I mean,
thank you.
Just one more question, Dr. Alex.
Yeah,
can you explain this spin operator?
Sigma x y is equal h bar sigma y, right, and z h bar over 2
Hello?
sigma z. Yeah, I mean, this is in I mean, this one for the axis x, this one for the axis y, and this one for the axis z. Defense, what question?
Yes, I was asking about this spin operator, why are we using this H cap operator means? How is that relevant in the calculation?
So we will discuss that in what follows. Here I just bring this example because it's uh, easy enough to make this practice here. Uh, how it relates to what? So basically, this spin operator as x, y, and z, it describes the spin state of a particle in the same way how the operator of momentum describes the momentum of a particle, or Hamiltonian describes the energy state of a particle. This spin operator describes the possible states of spin, and spin is well, it is angular momentum, right? It's some sort of artificial angular momentum of self momentum of the particle. Of course, we don't know what it is because the calculations says that it is not really like a real spinning, not real rotation. But the experiment tells you that tells us that we have to um, assign some sort of self angular momentum to these elementary particles. And of course, the spin can be like 1/2, right? This is for fermions, and it can be integer number like 1, 2. For example, 1 corresponds to a photon, and this is something that we know, the polarization of light. And by the way, the polarization of spin of an electron and the polarization of a photon with spin 1/2, all these effects are described by this spin operators as x, x, y, and xz. That's why I also put it here. So I'm not sure if it does, if it answers your question.
Yes, just a follow-up question, Dr. Alex.
Yeah.
Like my point is like the question says spin half along the x direction, right? What if it says spin 1 in the x direction? Does the formula changes according to that?
Not really get it. Can you explain your question?
Yeah, my point is like, is this formula of the spin operator remaining same for what spin value we are calculating? Like in the question, it says that we are calculating a spin of a particle with a spin 1/2 along the x direction. What if that is some different value apart from 1/2?
Yeah, it will be different. So that's what I said, or tried to say, that, for example, a photon has a spin 1, and in fact, up to some peculiarities, let's say this way, you can use the same matrices. And so fortunately, like all the particles that we deal with, they are either 1/2 or the 1, and basically that's it. Especially for this quantum computing, the vast majority of systems, they have either spin 1/2 or 1. And of course, there are some complex systems like molecules consisting of many particles, right? And then you have to sum up all the spins of all constituting elements of the particles, and then you'll have something like different. But for that, you also what you basically need this definition of spin operators. I mean, anyway, so this is just the problem to show how we, I mean, basically work with this operator and what are the eigenvalues of the of this operator. So let's go next to the postulate number 4. Postulate number 4. And I call this projective measurements. Projective measurements. So before we measure the system, we of course don't know like anything about the system, in what state the system is, and etc. And we have to take into account like all possible states of the system, and we have to write the state of our system like a superposition of all possible states, something like this, or something that we already wrote many times, right? And but when we do the measurement, what we actually do, we have some apparatus, right? The system that measures some state of a quantum system, and this apparatus, this equipment, is necessarily classical, because this is something that we used to this is something that we interact with, right? So we can interact only with the classical objects. So our measurement apparatus is classical, and the measurement in quantum mechanics is basically the interaction of quantum system with some quantum state. By the way, we will discuss a little bit more deeper what is quantum state in what follows, hopefully today. But I mean, in simple words, this quantum state means that the system is presented in all the possible states all together in the same time. So the measurement is the interaction of the quantum system with a quantum state with a classical system. And the classical system is, of course, a very complex system that consists of many, let's say, quantum subsystems, right? For example, like our apparatus of course, is made of billions and billions of electrons, atoms, and even though all of them have their quantum states, but when you put them together, these billions and billions particles, they lose their quantumness, and at some point your system starts behaving classically. So the system becomes a classical system. And so let's consider such a system, and then we do measurement. Let's write this measurement. And as a result of measurement, of course, I can get only one possible state, but not the superposition of them, just one possible state. For example, some state psi m. And according to the Born's rule, right, I'll get this state psi m with probability modulus cm squared. Then I can prepare this system again in this state and do another measurement. And in the result of this measurement, I will get something else. Another state, for example, psi k, for example, with probability ck squared. Then I can prepare the system again, do measurement, and in the result I will get another state with probability cn modulus square, and and etc. And I don't know with certainty, 100% certainty, what state I will detect in the measurement. I can only speak about the probabilities of finding that state or another state, just probabilities. And this probability is described by this c modulus squared. And how it looks like, for example, how you can imagine this situation. So let's say you have a Hilbert space with some basis. For example, this is psi 1, this is psi 2, for example, and this is some psi n, etc. And you have a system that is prepared in a state psi. And then you do measurement, you measure your system. For example, in this example that we discussed just 5 minutes ago, the Hilbert space is two-dimensional, so you have only psi 1 and psi 2, which correspond to the direction of the spin, either up or down. And then you measure the system, so you still have the same basis, the same Hilbert space, but after the measurement, you will get your result, your system in state, for example, psi 1 in this state. This is psi 1, this is psi 2, and this is some psi n, etc. So we call that, we say that the state is collapsed. The state is collapsed to one of the possible states, to one of the possible states. Collapsed. And this process, so technically, this process is not described by the quantum mechanics, because this is some sort of like a magic that happens due to the interaction of quantum system with like Fragile quantum state with the classical system that consists of billions and billions quantum subsystems. So basically, you measure the quantum system in some particular state, and the system collapses to one of the possible states, and after, like, then you remove your or you stop measurement, and and this quantum system will stay in this state to which it collapsed to, and it will be there for a while until you prepare your system in a general state once again. Yeah, so now yeah, so this state, this process of measurement can be this particular process of projective measurements, because there are other types of measurement, more like general one, and we probably will discuss that in what follows. But this one is kind of historically the most important one, is projective measurements. And projective measurements can be represented by so-called projective operators or projectors. Let's write this down. So projective operators, projective measurements can be represented by projective operators or projectors. So what is projector? For example, let's describe an operator like this: P operator, some index M, and this operator is equal to out product of some state psi m. So this is out product of this state psi m by itself. So this is basically a projector. How it works? So let's describe this general state psi. Let's consider this general state psi, and it consists of course, many states, right? This the superposition of all possible states. And now I apply this projection operator onto this state psi. So what I do, psi or PM state psi, and it's equal to this psi m, psi, right? And it's equal to this psi m. Then I can plug in this formula here instead of psi, and what I get? Oops. I'll get the sum over n. Cn is a constant, so I can take it out from the inner product, and here I will get psi m psi n. So, and you can recognize that already, that this inner product of psi m psi n is nothing but the Kronecker delta, which is mn, which is equal to 1 if m equals n and 0 otherwise. So it it becomes psi m, and what I get left c m. That's it. So the result of action of this operator m, this projector, on a general state is a constant times the particular state psi m. Right, the projection operator to the state m generates me only one state psi m multiplied by some coefficient cm. This is the result of the action of this projection operator. And if you recall this example with the spin, for example, the projection operator here would be, I mean, these spin operators as x, as y, and as z can be written as a projection operator of measuring the spin in a particular state. Very good. Do you have any questions?
No, Professor.
Yeah, and here I have a small aside, which is, by the way, important. Aside. So in quantum mechanics, any two quantities can be measured in experiment, in the same experiment. In quantum mechanics, any two quantities can be measured in the same experiment if and only if their operators commute. If their operators commute. So you remember that like in general, if you have two operators, like operator A and operator B, and you take a product of two. So, by the way, the product of two operators is meaningless without the function at which the operators act. So, like, in order to make it right, technically I have to write some function here. So, and consider this as the operator B acting on F first, and then operator A acts on the result of the operator B. But for now, we can remove this function here and simply write it in this way. So the product of two operators. So in general, the product of A and B operator doesn't equal to the operator B and A. For example, let's consider, for example, these x and px operators, right? The coordinate and momentum. So in the first case, for example, if A is x, B is px, then I will have something like x px times function of x, not times, but this operator acts on a function f of x, and the operator px is minus I h bar d over dx, right? And then it acts on this function of fx, and what I'll get minus I h bar x df x dx. This is the result of this operator x px here. But if I flip the operators, I will get something px times x and fx, right? And in this case, it will be minus I h h bar d over dx, and here x times fx, because the operator x is x. Yeah, and in this case, I have to take the partial derivative of this product of two functions, and definitely the result will be different. So in general, the operators in quantum mechanics they don't commute. They don't commute. And in order to describe this situation when the operators don't commute, we construct the following operator. Basically, the result of subtraction of operator AB minus operator BA. And this is nothing but the commutator. Commutator, we denote it by this rectangular parentheses, and operator A here, comma, operator B, like this. So this is the commutator. Commutator. And if commutator is equal to 0, then operators commute. If it doesn't equal to 0, then operators don't commute. And this aside says that in quantum mechanics, any two quantities can be measured in the same experiment only if their operators commute. So basically, if you measure some quantity A and quantity B in the same experiment, for example, you measure coordinate and momentum. So we discussed that coordinate and momentum don't commute. That means that you cannot measure them in the same experiment with 100% certainty. So in result, you will have some sort of quantum noise, and we will discuss this a little bit more in what follows too. And if the operators commute, for example, operator x and operator momentum y, let's say. So these two operators commute, and you can measure the coordinate and momentum in the axis y simultaneously in the same experiment. Do you have any questions regarding this part? So if no, let's go to the postulate number 5. Postulate number 5. And yeah, so finally this postulate number 5 is talking, like, it's telling us about the evolution of quantum system. So let's formulate this way. The time evolution of a quantum system let's put in parentheses in the pure state. In the pure state. We will discuss this notation pure state also in what follows. basically a pure state is a state that described by the state vector psi. And as we will see today, not all possible quantum systems described by this vector psi. But in the pure state, when we can describe the system by psi vector, the time evolution of a quantum system can be Oh, so sorry. Okay. So the time evolution of a quantum system in a pure state is governed by the Schrodinger equation. Schrodinger equation. Schrodinger equation. So let's postulate this equation, because basically Schrodinger equation was derived by Schrodinger. It was not derived, actually, it was kind of postulated first for steady state systems, and then generalized to systems with time, it's transient processes in time domain. So let's write down this equation. So it is I h bar, then the time derivative of the state psi. It is equal to the.
I have a question.
Yes. Mm-hmm.
It's related to the commute operator you told. I remember right now that there's Heisenberg uncertainty principle, right? It
Yes.
also says like you cannot measure two things at the same time, like position and momentum kind of thing. Is this related to that?
Yes, and yes, very good question. In fact, we will discuss this today, and this this basically says that uh, for any two quantities whose operators don't commute, then you cannot measure these two quantities with 100% like accuracy. You always have some uncertainty, and that uncertainty gives you some, we call this quantum noise. Your result always fluctuates. You measure the coordinate, for example coordinate x, and you try to measure the momentum px, and the result will be like fluctuating. The more precisely you measure coordinate, the more noise you get in the momentum, and vice versa. But this is not always the case. For example, if you consider the another um, projection of momentum, for example, to axis y, and you measure your coordinate x and momentum y, then their operators commute. So this commutator xpy will be equal to 0, and in this case you can measure this coordinate x and momentum py with perfectly. You can detect them without any quantum noise. Yeah, and we will discuss this in a while, hopefully today. But let's get back to this Schrodinger equation. So it is I h bar, the time derivative of state psi, and the result is equal to the um, the operator H, the Hamiltonian, forgot the name, Hamiltonian H times this psi vector. So this is the Schrodinger equation. Schrodinger equation. So here in this formula, this state vector psi is general state, and of course this general state can be represented as a superposition of some basis states, right, psi n, and since this equation is linear, the same equation holds for each particular eigenstate, for each particular eigenstate psi n. For example, I can write, similarly, I can write the same for the state psi n. So yeah, this is the similar equation, but this one is for the vector state, this psi state, and this second one is for the particular eigenstate psi n. This is the kind of tricky moment. The same way, sometimes people write this, without this cat-bra notation, you of course can sometimes write this simply by psi, and then your equation will be IH d psi over dt equal to the Hamiltonian psi. Sometimes people, instead of this d over dt, you can use the so-called Newtonian notation, when you simply put a dot over the letter, and the same equation would be I h bar psi dot to h psi. So this is the Newtonian notation for the derivative, and yeah, so this is just different basically a representation of the same formula, of this Schrodinger equation. And also let's recall this, the Hamiltonian that we derived in the coordinate representation last time. I'm talking about this one. So the Hamiltonian in coordinate representation is just a sum of kinetic energy plus potential energy operators. And we can use it here. So substitute this H, this Hamiltonian for for minus H bar over 2m Laplacian, right, and then plus the potential energy V. It can depend on coordinate and time in general case. So the result will be I H d over dt, the state psi, and it's equal to minus h bar squared over 2m Laplacian psi plus v rt state psi. So this is kind of textbook Schrodinger equation that you probably saw many times in the basic physics books, or maybe in the high school physics. Well, let's consider at this point, let's consider an example of so-called stationary states. Example. Stationary state. Stationary state, or also known as steady state. Steady state, stationary state. So what this is about, it's about a system without any interactions with external systems that don't belong to the one we consider. And in this case, this is so-called isolated system. So it is isolated system, right? It doesn't interact with other systems. And in this case, in the case of isolated system, the potential doesn't depend on time. And as a result, the Hamiltonian also the function of coordinate but not time. So this is the, for example, a classical problem of hydrogen atom. The Hamiltonian doesn't depend on time, and for such a system like an atom, we can basically simplify this Schrodinger equation as follows. So let's write down this Schrodinger equation for this steady state. For a moment, I use the like usual function presentation instead of Dirac notation. So let's write psi just as a psi, because I don't going to form any inner or outer products. So this psi, of course, is a function of coordinate, right? And now I take this time derivative of this function, partial derivative. And of course, it depends on time, but we will see that this dependence on time is just a harmonic dependence. So yes, then our Hamiltonian, which is time independent, and psi. So at this point, since this Hamiltonian doesn't depend on time, I can represent my psi as a product of two functions, phi, function of r, and kappa, the function of t. So the all transient dependence behavior is basically in this function kappa of t. And the coordinate is in this coordinate part of this function, right? So the product of two. And now I can plug in this ansatz to this Schrodinger equation, right? And what I will get, I'll get I h bar, then time derivative of phi. Psi, I take only time derivative of kappa. I can take this phi out, this phi of t out, then no, sorry, phi r, and then goes d kappa dt. And here the Hamiltonian depends on r only. That means that the function kappa that depends on t can be taken out from this from this operator, and I can write kappa t, then Hamiltonian, and phi r. Phi r. So now let's make an ansatz that my key kappa of t is a simple harmonic function of the following form. So e to the power of I over h bar E, which is energy, times t. And plug in this ansatz to this equation. So what I get? I get I h bar phi, then minus I over h e, then the function kappa itself, because this exponential function, right? And on the right hand side, I got kappa t Hamiltonian phi r. So now I see that I can cancel these two kappas on two sides. Here I have minus, and I squared gives me another minus, so it will be plus. And here h and h bar cancel out, so everything is simplified to to what? So basically the Hamiltonian R is equal to E phi R. Okay, so in this equation, my Hamiltonian now acts only the function that the special part of the state vector of the state function phi, and I don't have any dependence on time. And if I, for a particular system, I can write the Hamiltonian for this, like for an atom, I write the Hamiltonian. Then this equation, by the way, nothing but the eigenstate and eigenvalues equation for this particular operator H, for this particular operator Hamiltonian. And E here is the eigenstate, as you can see, eigenstate, and phi is E is the eigenvalue, and phi is the eigenstate. Because the action of operator H on the function phi is just the multiplication of this function phi by a constant E. That's why this eigenstate and eigenvalues. All right, so a particular system, I can write down this Hamiltonian, then solve this equation for eigenstate and eigenvalues, and then the total solution, this psi, which of course depends on r and t, will be the product of this phi r times the function kappa, which is this harmonic function e t. So this is the the total solution to the Schrodinger equation. And historically, this equation written here, this is the steady state Schrodinger equation. Steady state Schrodinger equation. Oh, it's not beautiful. This steady state Schrodinger equation was derived by Schrodinger first, and then generalized to another one, which is known as the time domain or time evolution Schrodinger equation, which is more general. Do you have any questions?
No, Professor.
Okay. And I have two notes, also pretty important ones. So let's name it note 1. So when I solve this equation, I will get some solution psi, right? This is the solution to Schrodinger equation. And in general case, this solution won't be normalized. But in order to use this Born rule, right, to describe this state psi as a probability amplitude, I have to normalize my final solution to 1, basically. So I have to the solution must be normalized to, well, in general, it must be normalized to the modulus of psi squared less than 1, less than unit. Yeah, so in general, the solution is not normalized, and when you found the solution, then you have to normalize it. And sometimes this normalization procedure is kind of, especially for simplest cases, this normalization procedure is more difficult than the solving of the Schrodinger equation itself. And the second note 2, is about boundary conditions. So as you probably aware, it is not sufficient to formulate the problem in terms of differential equation, right? As here in our case, the Schrodinger equation. So it's not sufficient to write down the Schrodinger equation. It is also must be accompanied by the boundary conditions. Boundary conditions. Boundary conditions, and the boundary conditions for the Schrodinger equation dictate that the both psi and the first derivative of psi by x, I mean by coordinate, must be continuous on or at abrupt boundaries. Must be continuous at abrupt boundaries. What it means, for example, if you have a boundary between two subspaces, right? And this is, for example, the axis x. And let's denote this coordinate x sub 0. And this is boundary. And then you solve your problem. And how? Basically, you find the solution in the first subspace, and then in the second subspace, and then you connect the both solutions on the both sides. So basically, for example, in the first space, the solution like this, in the second solution like this, and then these boundary conditions dictate that the psi x sub 0 minus delta x must be equal to psi x sub 0 plus delta x. And the same way for the derivative dx, psi x sub 0 minus delta x must be equal to this psi x sub 0 plus delta x. For delta x very small, right, going to 0. For vanishing delta x. Okay, so basically that means that at the boundary, your solution on the left and right side must acquire the same value. Not only the function, but also the the derivative of the function across this boundary. Very good. Do you have any questions? All right. So then let's go to the postulate number 6. And this is supposed to be, oh no, yeah, we have another 2. So postulate number 6. Postulate number 6. And this one is about the time evolution operator. Time evolution operator. Time evolution operator. And let's also discuss this Heisenberg picture. Time evolution operator and the Heisenberg picture. Time evolution operator and Heisenberg picture. So what we discussed so far in this part, the Schrodinger equation, the time-dependent psi state, and independent operators, all this relates to so-called Schrodinger picture. But we can also formulate basically the same in terms of so-called Heisenberg picture. And sometimes, quite often actually, this Heisenberg picture is more like preferential, or people use this modern Schrodinger picture. So, so let's start with time evolution operator. Time evolution operator. So let's postulate this, that time evolution operator is a following operator U, because as we will see, this is the unitary operator, and it gets two arguments, basically the final moment of time and initial moment of time. And it simply equals to the exponential function to the power of minus I over h bar, then Hamiltonian, and then this difference t minus t sub 0. So this is the time evolution operator. Time evolution operator. So first of all, let's check that this operator is unitary. Right. So for that we require that the product of this operator by its Hermitian conjugated operator must be equal to 1, right? So in our case it is e to the power of I h h bar Hamiltonian t minus t sub 0 multiplied by u dagger. Dagger means we take the complex conjugation. So in the exponent it will be plus I over h and h dagger, right? T minus t sub 0. But now we recall that the Hamiltonian is a Hermitian operator, which means that the h dagger is equal to h. So these two functions cancel out, and in result I get 1. So this operator this operator is unitary. And in fact, as a there is a theorem that says that I can represent any unitary operator as an exponential function to some operator, to the Hermitian operator A, something like that. If you take this operator and its Hermitian conjugated operator, you will get 1. All right. So this operator, this is unitary operator, and how it works. So basically, it works the following way. Suppose you have a state of your system in a time moment t sub 0. It can be initial moment of time. You, for example, prepared your system in the initial moment of time, and then you are interested in evolution of your system. What happens next? What happens next? And in order to figure out what happens next, you apply this operator t sub 0 on this state, and in result you will get the state in the later moment of time. In the later moment of time. So you had like a state in some moment t sub 0, right? And you need to know where your system will be in the moment t. So you multiply this state by this evolution operator, and the result will be the state of your system in the later moment of time. For this reason, this operator is also known as propagator. Propagator. So you see, there are like many words, right? Like this terminology: propagator, projector, operator. A lot of like new words, but you just need to get used to all this. So this is propagator. Propagator for a known state creates another state in the later moment of time, and this holds for any t sub 0 and t. But of important important case is when t minus t sub 0 is something very small. So this t is right the next moment in time. So t is equal to t sub 0 plus epsilon. I take my t sub 0 and add very small epsilon and jump to a very very next point in space, right? And in this case, I can simplify my my unitary evolution operator. It will be t sub 0 plus epsilon, right? It will be e to the power of minus I over h bar Hamiltonian and epsilon here. Epsilon is very small. Epsilon is very small. So, and here at this moment, I can call this the Taylor's formula for the Taylor series, right? When, for example, if I have the exponential function ex, I can tailor this formula for small x. It will converge very quickly. So I can take, for example, one or two the terms, or three at most. So the first one will be 1, then the second one is the argument itself, and then the x squared over 2, and etc. And so we assume our epsilon is very small, so the very first two terms are sufficient. So I can represent this operator in the following way. So it will be 1 first, and then this argument, which is minus I over h bar, then Hamiltonian and epsilon. So, and now I take my initial function psi t sub 0, right, and act on this initial function by this operator, this time evaluation operator with very small epsilon. What I'll get? I'll get yeah, let's go step by step. So it is u epsilon. In the result, you of course get the state psi in another moment of time, which is very close to the initial moment of time. And on the other hand, we have this operator here, which is 1 minus I h bar Hamiltonian psi, and all this is multiplied by psi of t. Psi of t sub 0, of course. Sorry. Okay, let's expand the brackets. I'll get psi t sub 0 minus I h bar Hamiltonian psi t sub 0 times epsilon. So now what I do, I move this part to the left hand side, and I'll get the following. So it will be the psi in the moment t minus the psi at the moment t sub 0, right? And it's equal to minus I over h Hamiltonian psi t sub 0 times epsilon. So now I can divide both parts by epsilon, and I'll get the final result, basically, over epsilon. It's equal to minus I over h Hamiltonian psi t sub 0. Very good. So now, what is this? This is the change of a function upon a small change of the argument, right? So this is nothing but the partial derivative of psi over t. And on the other hand, this is equal to this part on the right. So it will be equal to minus I over h Hamiltonian. And in this case, when we replaced this function change by the partial derivative, I have to write t here. So it will be this form. And now let's divide both parts by h and basically this prefactor here. And in result we'll get I h bar d psi over dt is equal to Hamiltonian psi which is nothing but the Schrodinger equation. So you see that the formulation of quantum mechanics and quantum theory in terms of time evaluation operator is completely like similar, fair, or equivalent to description in terms of Schrodinger equation, because this evolution operator, it contains this information about the Schrodinger equation in it. So you can use this evolution operator instead of Schrodinger equation. And sometimes it is more convenient to work with these propagators. Very good. And what is even more important is that, I mean, for our discussion, is that having this evolution operator, I can represent the quantum mechanics is in so-called Heisenberg picture. Heisenberg picture. So what is Heisenberg picture? So in the Schrodinger picture, we have the state of a system psi, which is time dependent. So it is a function of time, and all the evolution of the quantum system is basically sits in this function. At the same time, the operators, like for example some operator A, it doesn't depend on time. So all my dependence on time sits in the psi vector, but the operator, it is time independent. And for example, the value that we measure in experiment, what it is? It is a matrix element, something like this. This psi depends on time, then the operator and then psi depends on time, right? So this quantity, it is a matrix element in the state psi, and this matrix element basically gives you the the result of the possible result of the measurement. And this is only what you after, because operator is a mathematical concept. The psi vector is a mathematical abstraction, and this matrix element composed of two, nothing but the mathematical abstraction, but this matrix element provides you a number, and this number is something that you actually measure in the lab. So this is most important construction in all the in all this theory, because this is something, in some sense, this is only what has physical meaning and physical reality, the construction like this. And we will discuss like much more about these matrix elements and etc. But for now, let's know that in the Schrodinger picture, this psi state depends on time, but the operator is time independent. So this is Schrodinger picture. Matrix element in Schrodinger picture. Can we actually change this somehow to like to keep the value itself the same, so without changing this matrix element, so the result of measurement will be exactly the same, but represent this in the following way: as a psi time independent, psi at some moment in time 0, and then it doesn't depend on time. So it's just a value that doesn't depend on time. We set this time moment to be 0, and then don't follow this time dependence of psi. But instead, we change the time dependence to the operator. Like this. So the question is, can we represent this matrix operator in this way when the operator depends on time, but the state psi is time independent, so that these two matrix elements, they give exactly the same result. And I mean, of course, the answer is yes, and the matrix element written in this form is basically a matrix element in the Heisenberg representation, Heisenberg picture. How I do so? Well, I have this psi at time moment 0, and in order to get the psi at moment t, I have to multiply this by this unitary evolution operator u, right? So I do something like this, and my result will be psi t. Something like this. And if I take the Hermitian conjugation, what I will get? I will get psi t, then u Hermitian conjugation. Let's put this. This is the operator. and the result will be psi t bra. So now I can take these two and plug into the first formula, and I will get the following. The following. So it will be psi psi 0 u dagger, then a, then u, then psi 0 cat. And I require this result to be equal to this second one in the matrix element in the Heisenberg picture. So I conclude that my operator A in the Heisenberg picture is connected to the operator in the Schrodinger picture through the similarity transformation. This is what we discussed last week. The similarity transformation. Similarity similarity transformation. Well, yeah, so the Schrodinger representation and Heisenberg representation, they are completely equivalent. They produce exactly the same result, and they are connected through similarity transformation. So at this point, you might wonder why so many representations, because already discussed that we can describe a quantum system using different representations of different Hermitian operators, right? Hermitian operator generates the basis of eigenstates, and you can use any of these bases of eigenstates to describe your system. This is the first degree of freedom. Then this another degree of freedom of describing a system in terms of psi vector or evolution operator. Then this degree of freedom of describing in terms of Schrodinger equation and Heisenberg picture, Schrodinger picture, different approaches, and all these approaches give basically the same result. And the physical system itself, of course, doesn't depend on how you describe it. In some sense, it is close to the situation when, for example, even in classical physics, you choose one coordinate system and describe your system in that system. Then you can change your coordinate system to another one, and of course the result will be the same, but the solution will be different, and it may be this change can simplify the calculations. For example, when you describe, for example, the planetary system, the rotation of Earth around Sun, for example, right? You can describe this trajectory in the XYZ coordinate system, but this is actually very complicated problem. But if you change to well, spherical or elliptical coordinates, then your calculations are simplified significantly. The system is the same, representation is different, but in the second case, you get the result much easier. Here in the quantum mechanics, the situation is like very similar. And sometimes it's easier to solve your system in Schrodinger equation, Schrodinger representation. In other case, using Heisenberg representation would be easier. It can simplify the things, etc. So that's why we had to discuss these representations. And of course, in Schrodinger picture, we have Schrodinger equation, right? It is the most important equation in Schrodinger picture. But what about Heisenberg picture? Well, here we also have this, say, master equation, and let's derive this. It's very easy. So let's take, basically, let's take the partial derivative of this Heisenberg operator in time. What I'll get. Here, this operator A in Schrodinger picture doesn't depend on time. So I have to take the partial time derivative of u dagger and u. Right, so I write this derivative u dagger by time, and then operator A, operator u, and then plus u dagger A du dt. something like this. So now I recall that my u is nothing but exponential function minus I h the Hamiltonian times time. I assume that the initial time is equal to 0. It just provides some constant here. So the u dagger is what? It will be exponential function, complex conjugation, and then h dagger, but we discussed that h is Hermitian operator, so I can simply write h here and t. Very good. So from here I can find this time derivative of operator u. It will be minus I h here Hamiltonian, and then u itself, right? And now I take the the Hermitian conjugation of this to get my time derivative of u dagger, and the result will be plus I over h, and then you remember when I have two operators A and B, right, and take the dagger, I have to write B times A dagger. So in this case I have H and U, so the result will be U dagger times H. U dagger times H. So now I can plug in these two formulas to this one, and I'll get what? I'll get I over H, U dagger, H, then operator A, then operator U, and then minus I over H, U dagger A, H, u equals to, let's go here. So it will be equal to, I take I over h out from the brackets, right? And here I will have u dagger h a u minus u dagger a h u operators, of course. All these are operators. So now I see that here I have u dagger on the left, u on the right, here u dagger on the left, u on the right. So I can rewrite this as follows: I over h, then u dagger here, then the parenthesis h a minus a h and u here. So here, this guy in the parentheses, nothing but the commutator. So this is the commutator of Hamiltonian and the operator A in the Schrodinger presentation. And so the result of all this is what? So the time derivative of my operator in the Heisenberg picture is equal to I over h u dagger, then the commutator h and a, and then u. So the commutator is just an operator, and the fact that I apply this u dagger and u on the left and right side, this is another similarity transformation, but applied to the commutator of 2. So I can simply write this the following form. In the following form: I over h, then this commutator h a in the, let's put Heisenberg h here. So basically this commutator in the Heisenberg picture. So usually this Hamiltonian, it doesn't depend on time, and the only operator that changes when we change the picture is only this one, this operator A. So usually this can be written in this form: I over h, and here this Hamiltonian and the operator A depending on time. So this is the Heisenberg operator. Okay, so this is so-called Heisenberg equation. Heisenberg equation. So yeah, just as a summary. So in Schrodinger picture, the psi state depends on time. That's why we have this Schrodinger equation that tells us how the state changes in time. Sorry, I just need to connect my tablet to charge. That's why the state depends on time. That's why we have this Schrodinger equation that defines the state of time in the state of system in any moment in time. But the operator in the Schrodinger picture doesn't depend on time, and of course stay the same. So we don't need any equation for time dependent time to calculate, to describe the time dependence of the operator. In the Heisenberg picture, the story is like completely opposite. It is the state vector is unchanged. It doesn't depend on time, but the operator changes in time, and this Heisenberg equation is the main equation that governs the dependence dependence in time of the system. Do you have any questions? If not, yeah, let's proceed to the to the next one, which is called the uncertainty relation. So the postulate number 7 uncertainty relation or uncertainty principle. We already discussed a little this uncertainty principle today, and in the simplest form, and historically the first one was the following, invented by Heisenberg also. So historically the following Heisenberg uncertainty relation appeared. So it provides the the connection between the uncertainty in coordinate and uncertainty in momentum in the same axis x in this case. So the product of these two is more than or larger than h bar over 2. Uncertainty relation for coordinate and momentum px in this case. So what are these delta x? Delta x is simply the x itself minus the mean value of x. Let's denote this mean value this way, the angular brackets. So mean value, and the same way the delta p x is px minus mean value of px. So basically this is the measure how the result of measurement, right? For example, this is x as a function of, or I don't know, like let's say this is the result of measurement, and this is the number of measurement, the number of measurements, and and for example, you get something like this. So this will be the mean value, right? This mean x, or you can say this is the expectation value. Expectation value, this is the most like the value that you expect to measure when you do a lot of number of measurements, mean value. But in result, I mean, as a result, in each particular measurement, you can get something here or here, and this delta x represents the dispersion, right? The dispersion of the actual result around the expectation value, because the same result, the same experiment for another system can get something like this, and again this would be another expectation value, but now the dispersion will be much larger. So dispersion tells you how the result is dispersed around the mean value, the mean value. And this uncertainty relation simply tells you that this is the product of two, right? This is the product of the dispersion x and dispersion px, and this product must be larger than half of the Planck's constant. And it means that if you measure, for example, the coordinate, you will get more larger dispersion in momentum, and vice versa. If you measure momentum more precisely, that means that your dispersion in x will be larger. So for example, how you can imagine this situation. For example, you have a screen with a slit like this, and if you have a particle that travels towards this screen, if the particle passes through the screen, you say that, oh, your particle is located up to this slit size, right? This delta x. But when this particle passed through, you of course get this scattering effect when your particle starts propagating to some angles, right, to different paths with some angular distribution. And you of course cannot say what way this particle goes. But then you make this slit smaller, much smaller, and do the same experiment. A particle travels to this slit. So now this delta x prime is much smaller, and you can expect to you can expect to detect this coordinate of the particle with a higher certainty, like higher accuracy. But according to this uncertainty principle, what you will get in return is larger uncertainty in k. So basically your wave will propagate in a larger set of directions, to a larger angle. And this is like illustration how increasing in the detection of the particle in a particular place, right, increases the uncertainty in the momentum of the particle. But what about, like, I mean, this is the uncertainty relation for coordinate and momentum, but there are many different pairs of quantum quantities. Can we derive something more general? And the answer is, of course, yes. And let's derive this general uncertainty relation the following way. So let's consider so-called standard deviation. The standard deviation is standard deviation. Standard deviation. So standard deviation for an operator A, for example, it is quantity like this: sigma, basically the dispersion to the power of 2. Sometimes we denote this by delta A to the power of 2, delta A squared. And by definition, it's equal to the mean value of this difference of the operator A minus mean value of A square. Right. So this operator minus mean value of the operator, this is the dispersion. And then I take the square of this dispersion, and after that I do the average operation, the mean value of the of the result, mean value of the result. And so let's defactorize this this equation. So what I will get the mean value of A squared, right, then minus 2A A mean value, expectation value, then plus expectation value squared, and mean value of all these terms. So I'll get the expectation value of A squared, then minus 2 expectation value squared, plus expectation value squared. So these two simplify, and I'll get expectation value of A squared minus squared of expectation value. Right. So this is the standard deviation. This is standard deviation. For another operator B, I can write the same, basically this deviation for the operator B, and it will be by definition it will be operator B minus expectation value B squared and mean value of this result, right? So so let's describe this in detail. So I have this standard deviation squared, which is this one, right? And when I find this mean value, this is nothing but the finding the matrix element in some state, in some arbitrary state psi. So it will be psi here, then a minus a mean value squared psi. Very good. So now I can represent this part as a minus a expectation value times a minus a expectation value. So it will be equal to psi bra, then a minus a expectation, another a minus a expectation, and then and then psi. Well, I see that this construction basically consists of two vectors. So this one vector here, it is operator a minus expectation value a, and it acts on a vector psi on the left, and this another one that acts on the same vector on the right. And since this operator a is Hermitian, these are basically the same vectors. So this is the vector, let's denote it a cat, then this will be a bra, and the result will be this inner product a. If you don't understand anything, just interrupt me at any point and ask your questions. But this is supposed to be pretty clear, right? And the same way for the vector, for the operator b, for the deviation of deviation of operator b, I can do basically the same thing, and in the result I will get something like this inner product of b and b, where vector b is b capital minus b expectation times the same state psi. All right. So now for the following, I will need two inequalities. Two inequalities. The first one is known as Schwarz inequality. Schwarz inequality. Schwarz inequality. So it's a pretty very well known inequality in vector algebra, which basically says that the product of the inner product of two vectors, like vector a times vector b, inner product squared, is of course smaller than the inner product of each vectors, right? So the inner product of two vectors always smaller, less than the product of lengths of two vectors. Why? Because the inner product is nothing but the projection of one vector on another one vector, and the product of two lengths of two vectors, of course, is always larger than larger or equal to when the inner product of two vectors, and they're equal to only when the vectors are collinear. In this case, the length and the projection basically the same thing. But for us in our Hilbert space, right, we have to change this to the inner product of this Hilbert vector space, which is the vector A times vector B, right? So this is this part. It must be larger than the product of A, B modulus squared. Right, so this is for this in our case. This is always true. This is always fair. And the second inequality, is even more like straightforward. It basically says that the absolute value of any complex number is larger or equal to the imaginary part of this complex number squared. Why? Because the complex number is a sum of imaginary and real part, right? And if you take the modulus squared, it is z times z complex conjugation, right? And the result is equal to real part z squared plus imaginary part z squared. And of course, this part, this absolute value squared, is always larger than imaginary part squared on a value of the real part. And if real part is 0, then the absolute value z is equal to imaginary part of absolute value z is equal to imaginary part of this complex number. So this is very very easy to get. So now let's use these two inequalities to represent the product of of two vectors that we just derived. So the first one is a, right? Now I take the product of this with b. And according to this first Schwarz inequality, it must be larger than the absolute value of the product A times B, right? In the same time, this is this A times B is the complex number, and I can represent this complex number. I can find the imaginary part of this complex number. So the imaginary part of this complex number, it will be 1 over 2i. So you remember that imaginary part of any complex number is the number itself minus the number complex conjugated divided by 2i. So that's why I put this 2i here. And then the complex number itself, which is a, b, right? And then minus number complex conjugated, which is BA. And this Z squared, so I get this squared. So this of course must be larger than, right? So this is larger than. That means that this part is also larger than this part here. Larger or equal to. So this product A times A is nothing but the standard deviation of operator A. This B times B is the same way standard deviation of the operator B. And our goal to find what is the product of these two, and it's larger than this part here, and we just need to calculate this part. So let's go ahead for that and find this A times B. So for the A times B, I recall that my A is the psi vector, right? We introduced this notation here. So it is a psi, then operator A minus expectation value, right? And for the B, I have B operator minus expectation value B, and the same state psi. So now I can open the brackets, defactorize the things, and I'll get what? This psi here, then operator A times B, A expectation B, and the same way here. So I'll get what? I'll get A operator B operator, then minus A operator expectation B, then minus B operator expectation A, and plus the product of two expectations. All this in brackets and and psi. So now let's open this parenthesis, right? So it will be psi, then a b psi, then minus b expectation is a constant, so I take it out from this operation, and here we'll get psi a operator psi, then minus the same way expectation a, take it out. Here I'll get b psi b psi, and plus finally the expectation a times expectation b. There are two constants. I take it out, and here we'll get this inner product of psi times psi, which is of course 1, because the state is orthonormal. Right, so I get, this is the expectation value of A and B, then minus expectation B expectation A, then minus expectation A expectation B, and plus expectation A expectation B. So these two guys cancel out, this one and this one, and the result of what it was A times B. The result is the expectation value of these two operators A, B, minus expectation A, expectation B. Very good. So, but for the for this formula here, we need the another one, this product B times A. And for this one, by symmetry, I can write the result. It will be expectation of B times A minus expectation B, expectation A. But this is just constant, so it doesn't matter in which order what order you write it. So hence the difference of two, B, A, B, is equal to the expectation of AB minus expectation of B, A, and these two guys cancel down. And so yeah, let me write this here. A B product minus B A product is equal to expectation AB minus expectation BA, right? And this is equivalent to the operation of taking the expectation of AB minus BA due to the linearity of this operation. And now I know that this forms the commutator of these two operators A and B. So I conclude that this difference is nothing but expectation value of the commutator A and B, these two operators. So the result of this formula is delta A squared delta B squared larger than 1 over 2i, expectation value of the commutator A and B. Oops. Expectation value squared. And taking the square root from both parts, right, I conclude the final result is delta A times delta B is larger than or equal to 1 over 2i expectation value of this commutator A and B. This is the this is the main result, and actually I can even put this in a red frame. So this is the most general uncertainty relation known in quantum theory. And of course, as an example, let's consider A the coordinate and B the operator Px, which is minus I over minus I h d dx, right? So first of all, let's find this commutator x and Px. And again, when I calculate the commutator, I have to apply this operator on some function psi. Let's do this. The function psi. So here I have x times Px operator minus Px operator times x, and all this operator acts on a function psi. Okay, So now for the operator px, I substitute this formula here, and I get x then minus I h d over dx psi, right? And then plus I h d over dx, and here I have x and psi. So the first term is minus I h x d psi dx, and that's it. I cannot simplify it further. But the second one, this plus I h, this is dx of x times psi. So this is the time derivative of psi by x times the first one, psi dx, plus the psi constant over dx. So dx over dx is 1. Sorry. And and I noticed that these two guys this equal, but the up to the sign, so they cancel down, and the result is equal to I h psi. So the commutator x px psi equals to I h psi. That means that the commutator x and px is equal to a IH. This is kind of remarkable result. So now I can go ahead and plug in this here. I mean, expectation of constant equals to the constant. So I no need to take the expectation value of IH. So I will get delta x times delta px larger or equal to 1 over 2I times IH. I cancel down, and it's equal to h over 2. So delta x times delta px larger or equal to h bar over 2. This is the formula we started with the this discussion. So it's very very important one, because this formula allows you to calculate the uncertainty principle for any two quantity who those operators don't commute. If the operators commute, like for example x and py, as we discussed, in this case the commutator is equal to 0, and then uncertainty relation says that you can measure the two quantities simultaneously in one measure, in one act of measurement. All right, I guess it is very good moment to stop. Next time we will finalize these basics of quantum theory. I will tell you about the density operator. It will be postulate number 8, I guess, called the density operator. We will discuss this density operator, why we need this, and how it works, and this is actually like even more general way to present or build quantum mechanics, because in contrast to psi function or psi vector, which is not always applicable to different systems. For example, some so-called open systems, they don't describe by psi vector. Also systems that consist of different interacting subsystems, they also don't describe by psi vector, and for that reason we need to bring this concept of density operator. And density operator like is even more fundamental one. And if you like go and read any paper published now about this quantum computing, quantum physics, most likely you will see that all the results description is based on the formalism of density operators. That's why we have to dedicate some time to go through this, and next time we will discuss a couple of the most important systems, let's say, in quantum mechanics, including the qubit, and after that, the week after, we will discuss we will start discussing the quantum computing with all those quantum gates, etc. All right, so let me start the recording, and I can answer any question if you have any.